let n be a positive integer, then x squared plus 1 is a factor of 3 plus x to the 4 to the n minus x squared plus 3 to the n times x squared minus 1 to the n for some options describing n. Okay. Like, ooh, wow. So let's start by writing out exactly what it means for a polynomial to be a factor of another polynomial. Okay, so if there is some polynomial p of x which satisfies this for all x, then we say that x squared plus 1 is a factor of this thing. Now there's all these relations between polynomial factors and coefficients of polynomials and so on that I don't know all of those things. So I'm starting to think instead maybe I substitute some values of x here and just narrow down when this can possibly be satisfied for all values of x. So the first obvious candidate here is to let x be equal to 0. If x equals 0, then I have 3 to the n minus 3 to the n times negative 1 to the n is equal to p of 0. And this, of course, needs that n... Oh, wait, hold on. I should have... this p is allowed to depend on n as well. The other factor could change depending on what n is. Okay, so Pn of 0 is this expression, and this is what, this is simply 0 for n even, and it's 2 times 3 to the n for n odd. Another good candidate that I could potentially substitute in here is x equals 1, because I note that this is going to be equal to 0 then, this term. So let's let x equal 1. Then I have 4 to the n minus 0 is equal to Pn of 1 times 2. I don't know if this is actually going to get me anywhere. I certainly don't want to expand. Maybe something I can do is combine those under a single power of n. So if I write this as 3 plus x to the 4 raised to the n minus x squared plus 3 times x squared minus 1 all to the n. So I have 3 plus x to the 4 minus x to the 4 plus 2x squared minus 3 to the n. No, that's not equal to 0. I mean, we need this to be equal to something times x squared plus 1. I'm not sure what I'm missing here. Like what, I don't really want to expand these things in any general sense. These things raise to the power of n. And of course, the leading power here, x to the 4 is going to be raised to the n. This x to the 4 is raised to the n. So there's no x to the 4, or x to the 4n. What am I missing? Okay, here's what maybe is the key. X squared minus 1 is equal to x minus 1 times x plus 1. And so if I raise this to the n, we just get that. Yeah, I don't think this helps either. What if I try is x squared plus 1 a factor of x to the 4 plus 3? Like, no, I don't think so. I don't know what idea is it that I'm missing here? Okay, let's see what happens if I just let n equal 1. So this is clearly not, x squared plus 1 is clearly not a factor of this, right? If I write negative 2x squared plus 6 is equal to p of x times x squared plus 1, then p of x has to be a constant, because otherwise the powers don't really match. So let's just call it p. So negative 2x squared plus 6 is equal to p times x squared plus 1. But then I get p is equal to negative 2 and p is equal to 6. So that's a contradiction. So n is equal to 1 does not work. Let's see what happens with n equals 2. Again, like there's got to be a better way of seeing this without expanding all this stuff. What if we just look at the constant term? Okay, in fact, let's call the left-hand side, let's call this polynomial 3 plus x to the 4 to the n minus x squared plus 3 to the n, x squared minus 1 to the n. Let's call that qn of x. Then the constant term of this is what I get when I substitute x equals 0. 3 to the n minus 3 to the n negative 1 to the n. And we saw that before. So yeah, we figured this out before also, right? This means that the constant term of the polynomial p of n must be equal to 0 for even n, or 2 times 3 to the n for odd n. What will be the degree of each side of these polynomials? How do I find, is there a way to find the leading term of a polynomial, the leading coefficient? Okay, so I've just worked it out explicitly for 2, and it does work. This is the other factor. But I don't see like the general pattern which is emerging here through this. So the answer is definitely not. So the answer is B, by process of elimination. I typically don't like to solve these questions through process of elimination and actually figure out what is going on. But it can't be A, because we showed that for n is equal to 1, it does not work. It also shows for that option C does not work. Option E does not work, because for n equals 2, it is correct. I mean, I guess technically option D, it might be true for all values of n greater than or equal to 3. But I suspect for odd values of n, it doesn't work and only works for even. So that's my answer. I don't know why I'm struggling to find out the general idea here. I've tried substituting specific values of x, but that's just going to give you at best specific values of this. So unless you can then derive a contradiction somehow. The other thing that I thought about is, if I can find out what the remainder is when x squared plus 1 divides that, and the remainder when x squared plus 1 divides that, then that'll be something that depends on n. But the remainder when it divides the difference means that, it has to be the difference of those remainders. But I don't see the easy way of figuring that out. What is the remainder of this thing for a general value of n? I know there's all these ways of relating remainders to what happens when you evaluate these polynomials at particular values of x and so on, but I just don't know what those are off the top of my head, at least, although I think I'm essentially kind of leaning towards them here. The other thing that even crossed my mind is let's substitute roots of this polynomial, of which we would then have to go to complex numbers and so on, and see what happens to the left-hand side of this equation. If I let x be equal to I, in fact, maybe let's do that. Let's go like this. So let's suppose we do then have a factor like this. I'm going to let x squared be equal to -1. So x is imaginary, that's fine. So then here I have 3 plus 1 to the n minus -1 plus 3 to the n and -2 to the n has to be equal to 0. So I have 4 to the n minus 2 to the n times -2 to the n is equal to 0. Okay, well this of course only works for even n. But that might not be the whole story. Or maybe it is. Maybe so this eliminates odd values of n. Odd values of n cannot work. But does this guarantee that all even values of n does work? I'm not sure. Yeah, I don't know why this one's got me stumped. Maybe it's just it's too hot in my apartment and I'm too tired. But yeah, this is the correct answer by the process of elimination. But I feel like I'm a little disappointed that I don't really totally understand a nice general way of approaching this. But if I think of something later on which it would be a better approach to this problem, then I'll write it down in the description of the video. Thanks for watching.